Okay, so welcome to the second lecture of week 7, and last week we began with chapter 2 and we gave what's the definition of the convergence of a sequence with a certain real limit. Then we saw some examples of convergent and divergent sequences, and then we mentioned that the rest of this chapter 2 on sequences and their convergence is going to be about theorems which allow you to deduce the convergence of a sequence without having to go through the definition. And we mentioned one such theorem which we have not yet proved, which I've written over here, which says that bounded and monotone sequences are convergent. And we began the discussion of this theorem by first explaining what's meant by a bounded sequence. So we learned last time that a sequence an is said to be bounded if there exists a positive number m such that for all the indices the absolute value of the nth term is less than or equal to m. So all the terms lie in a strip, so below a certain level m and above minus m. And we saw some examples of bounded and unbounded sequences. So I want to continue with that theme of examples and cover one more example where it's not very clear that the sequence is actually unbounded. Okay, and this is the example where we are going to look at this sequence where the nth term is given by 1 plus half plus a third all the way up till 1 by n. Okay, and we are going to show that this sequence is not bounded. So we had met this sequence earlier and we had noticed that the terms are increasing, because if I look at what is an plus 1 minus an, then I'll have 1 by n plus 1, which is a positive number. So each time the terms of the sequence are increasing, but the increment is very small if you go far out in the sequence. So for example, at the millionth stage, you will be adding 1 divided by a million, you see. So it's a very, very tiny increment. So it's not clear if you give me any large real number, then the terms of the sequence will eventually exceed that. But in fact, that's what happens. So this sequence is not bounded, and we are going to show that. Okay, so I have labeled this example with a star because the proof involves a little bit of a trick, but actually we'll see that it's in some sense quite natural. And I've summarized this example by saying that the harmonic series diverges. So don't worry about harmonic series, that's just the name given to this context. And the divergence part, right now we are just showing that this sequence is not bounded, but we'll soon see that then it also implies that it is not convergent. Okay, and the way we will see that this sequence is not bounded is we will prove this estimate. So we'll look at the terms with the index which is a power of 2. So I look at a2, a4, a8, a16 and so on, and in general we will show that a with the index 2 to the power n is bigger than n by 2. And the way we'll do this is a to the power 2n of course has a lot of summands. It's 1 all the way up till 1 by 2 to the power n, but we will group these summands in a special way and show that then each of these groupings is bounded below by a half, and we'll see that the number of these halves is equal to n by n. So we will get the estimate that a2 to the power n is bigger than n by 2. Okay, so that's the little bit of a trick, but we'll see that it does the job. So once you have this estimate, then it's clear that this sequence can't be bounded, because if the sequence was bounded and say bounded by some m, then the mod of a to the power 2n would also be bounded by the same m, right? Because all of these are positives and this is just a term, so the mod of that, which is itself, is less than m, and then that m would be bigger than n by 2 for all n's. But that is absurd. That's like saying that n is always less than 2m for all natural numbers, which is false because of the Archimedean property. Okay, so once we prove this estimate, that's the main bit, then we are done. So let's prove this estimate. So I'm going to look at the term with the index 2 to the power n, and that is given by 1 plus half plus a third all the way up till 1 by 2 to the power n. But let's write down the summands in a bit more detail because we are going to group them in a particular way. So I have 1 plus half, and then the next two are going to be grouped together. So that's why I've highlighted them in yellow. So I have a third plus a fourth, and then the next four are going to be grouped together and going to be estimated. So I have 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. Then the next 8 are going to be grouped together. So that's this yellow bit again. So I have 1 by 9 plus all the way up till 1 by 16. And then somewhere down the line I have 1 by 2 to the power n minus 1. And then I have 1 by 2 to the power n minus 1 plus 1 all the way up till 1 by 2 to the power n. And then this last part starting from this term 1 by 2 to the power n minus 1 plus 1 up till 1 by 2 to the power n is this pink bit, which will also be grouped together to be estimated. Okay, so how many terms are there in this last pink bit? Well, this 2 to the power n is really 2 times 2 to the power n minus 1. So it is, this denominator is really 2 to the power n minus 1 plus 2 to the power n minus 1, and you started off at the denominator 2 to the power n minus 1 plus 1. So this 1 is increasing up till 2 to the power n minus 1, right? And so there are 2 to the power n minus 1 terms in this last pink grouping. So, and then it's quite easy because to get the estimate, because in each of these groupings, which are highlighted in different colors, you replace each of the summands by the smallest. Okay, so 1 by 3 and 1 by 4, we note that 1 by 3 is bigger than or equal to 1 by 4. So each of these you replace by 1 by 4. So 1 by 3 plus 1 by 4 will be bigger than or equal to 2 times 1 by 4. Similarly, 1 by 5 is bigger than or equal to 1 by 8, 1 by 6 is bigger than or equal to 1 by 8, 1 by 7 is bigger than or equal to 1 by 8. So if I replace 1 by 5, 1 by 6, 1 by 7 by 1 by 8 also, then I get that this pink grouping is bigger than or equal to 4 times 1 by 8. Similarly, the next 8, I replace all of them by 1 by 16. So this yellow grouping is bigger than or equal to 8 times 1 by 16. And all the way up till in this last grouping, there were 2 to the power n minus 1 terms. And I replace each of the summands by the smallest one, which is 1 by 2 to the power n. So I get 2 to the power n minus 1 times 1 by 2 to the power n. Now notice that in each of these, you have 2 times 1 by 4 is half, 4 times 1 by 8 is a half, 8 times 1 by 16 is a half, and similarly this is also half. Right? This cancels against this, leaving a 2 in the denominator. And how many of these halves are there? Well, just look at the denominators. The denominators are 2, 4, 8, 16, all the way up till 2 to the power n. And this 2 is really 2 to the power 1. So it starts at power 1, goes up till power n. So there are n of these terms and n of these halves. Okay, so you have got that all of these is n by 2, and so I have got the 2nth term is bigger than n by 2, right? Because 1 plus n by 2 is certainly bigger than n by 2. And then we are done, because if the sequence were bounded and if there were a bound, then this would be less than that m. Yeah, and then we would get that for all natural numbers n is less than 2m, which violates the Archimedean property. So, but nevertheless, let's write down the proof just for the sake of completeness. So suppose that the sequence is bounded and then there exists a positive m such that for all the terms, the modulus of that is less than or equal to this bound m. So in particular, the terms with the indices 2 to the power n, where n is any natural number, is also less than or equal to m. Okay, but now that I have got this m, I take as my y 2m, as my x I take 1, which is a positive number, and so by Archimedean principle property, there exists a natural number capital N such that n times x is bigger than y, that is n times 1 is bigger than 2m. So now the mod of this term with the index 2 to the power this capital N is on the one hand bigger than n by 2 because of this estimate that we proved, and on the other hand it is less than or equal to m because the sequence we have assumed is bounded. Okay, and this m is 2m is furthermore less than this capital N by the choice of this n delivered by the Archimedean property, and this simplifies to capital N. So what we have got at the end of the day is this capital N is strictly bigger than capital N, which is absurd by the trichotomy law, and so we have got a contradiction, and this contradiction arose because we assumed that the sequence is bounded. So that can't be true, and so the sequence whose nth term is given by 1 plus half plus 1/3 plus so on up till 1 by n, that sequence is not bounded. Okay, so this was not very obvious intuitively because the increments were very, very small, so it was not clear that if I take 1,000,000 then the terms stay below 1,000,000. No, actually if you wait long enough, after a long time it exceeds this million, or any real number for that matter. Okay, so this sequence is not bounded. Alright, so now what I want to do is to show that every convergent sequence is in fact bounded. Okay, so the class of convergent sequences is contained in the class of all bounded sequences, and this is sort of intuitively obvious because what's a convergent sequence? A convergent sequence has a limit L, and the terms of the sequence are settling down to that limit. Last time we saw that it means a precise thing, and in particular it stays, for example, if you go far out in the sequence, we are guaranteed that it's at most at a distance of 1 from the limit. And that means that the terms beyond a certain index, they are all bounded, right? Because they are at most at a distance of L, so they are sort of stuck to L, right? On the other hand, what's left out is just a few of these terms, and then we can just take to get a bound, we can just take the maximum of these first few terms which are left out. So it's clear that the sequence is going to be bounded, and let's now write down the proof a bit more carefully. Okay. So the pictorial view is that, well, if this were the limit, and if I take my distance equal to 1, there is nothing magical about 1. You can take it any number you want to, but 1 is nice and positive, so why not take 1? And then we know that all the terms are sort of stuck to L at most at a distance of 1 beyond a certain n. So all the terms then lie in this strip. So they are certainly below this top line and also above this line. And what's left out are just the first capital N terms, A1 up till A capital N, and then to get a bound for that, you can just take the maximum of mod A1 up till mod A capital N. So let epsilon be equal to 1, which is a positive number, and then by virtue of the fact that the sequence is convergent, there exists a index capital N, such that beyond that index, the distance of the nth term to L is less than epsilon, which we have chosen to be 1. And then the terms beyond this capital N are bounded. So why? Because for every little n bigger than capital N, now I want to produce a bound for mod An. Now all I know is that the distance of An to L is at most 1, and somehow I want to create a bound for An. Well, I don't see a L over here about which I have some information. So why not artificially create a L so that then I can use this inequality. So I add and subtract L, and then this is less than or equal to, by the triangle inequality, the mod of this part plus the mod of this one. So it's less than or equal to the mod of An minus L plus the mod of L, but mod An minus L is less than 1 because little n is bigger than capital N, and this is just the same. So I have got a bound, namely 1 plus mod L for A capital N plus 1, A capital N plus 2, A capital N plus 3, and all of those. Okay. So what's left out? Well, just An, mod of An for n equal to 1 to n. But then the mod is, of course, less than or equal to this finite number, which is the maximum among all of these, mod A1 up to mod An. So for little n bigger than capital N, I have this bound, and for little n less than or equal to capital N, I have this bound. But I would like to have a common bound, some big capital M. So I just take that capital M to be the maximum of these two bounds. So I set capital M to be the maximum of mod A1 to mod An, and then I also put this in, 1 plus mod L. Now 1 plus mod L is certainly positive, right? Because mod L is non-negative, and so the maximum of these will of course be bigger than 1 plus mod L, which is positive, and so this is certainly bigger than 0. And the mod of each of these is of course less than m, and also 1 plus mod L is also less than m. So now we have got what we wanted, because by these two things we have that for every index little n, mod of an is less than or equal to m. Why? Because, well, for the first n it's less than or equal to this thing, yeah, but that's furthermore less than equal to capital M, and moreover for all the indices beyond this n we have that mod an is less than this thing, which is certainly less than again this m, because m was maximum of that plus other things, so it can only be bigger. Okay, so this shows that this sequence is in fact bounded. Okay, so every convergent sequence is bounded. That's what we have proved. So now, since we showed that this sequence whose nth term is given by 1 plus half plus 1 by so on up till 1 by n is unbounded, it cannot be convergent, because if it was convergent then it would be bounded, but we showed that it's not bounded. So automatically we know that this sequence is in fact a divergent sequence. Okay. So far what we have seen is that whenever a sequence is convergent, it is bounded. So it's a natural question to ask, is the reverse implication true? Are all bounded sequences convergent? And the answer is no, because for example the alternating sequence is certainly bounded, so minus 1, 1, minus 1, 1 and so on, but we saw that it is not convergent, right? So although it's bounded, it is not convergent, so this reverse implication is not true. However, we will now prove the theorem that if in addition to being bounded, if it is monotone, so either it's the sequence is increasing or if it's decreasing and it's bounded, okay, then the sequence is convergent. Okay, so bounded and the sequence being increasing allows you to conclude it's convergent, or bounded and the sequence is decreasing, that allows you to conclude that the sequence is convergent. So before we prove this theorem, let's properly state what's meant by a sequence being monotone. So here are the definitions. So let an be a sequence, then the sequence is said to be increasing if for every n you have that an is less than or equal to an plus 1. So a1 is less than or equal to a2 is less than or equal to a3 and so on. So all the terms are increasing, the terms of the sequence are increasing and the terms are sort of going up. Okay, and of course we allow them to also be equal to the next term. Okay, so it can be constant also. And the sequence is said to be decreasing if for every n, an is bigger than or equal to an plus 1. So the you have a1 is bigger than or equal to a2 is bigger than or equal to a3 and so on. So the terms are going down. Okay, and the sequence is called monotone. So this is a collective term for increasing or decreasing, if the sequence is either increasing or it's decreasing. So to get familiar with this, these notions, let's see some examples. So let's look at the constant sequence. So suppose C is a fixed real number, and then I take the sequence C, 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 and so on. Okay, so the constant sequence. Is the sequence increasing? Yes, because we allow equality over here, right? So constant sequences are allowed. Yeah? Similarly, the sequence is also deemed to be decreasing, again because we allow equality. And is the sequence monotone? Yes, because it's increasing, for example. Okay. Let's look at this sequence, the sequence of natural numbers. Is the sequence increasing? Yes. Is the sequence decreasing? No. And is the sequence monotone? Yes, because it's increasing. Now let's look at the sequence 1 by n. So you have 1, half, a third and so on. So it's clear that the sequence is strictly decreasing. Yeah. But it's not increasing. And is it monotone? The answer is again yes, because it's decreasing. So far all our sequences were monotone, right? Either increasing or decreasing. But now here's an example of a sequence which is not monotone. So it is neither increasing nor decreasing. You have minus 1 to the power n divided by n. The terms of the sequence are minus 1, half, minus a third, a fourth, minus 1 by 5, and so on. And now we see that the sequence is not decreasing, because you see the second term is actually bigger than the first term, and the sequence is not increasing either, because the third term is actually smaller than the second term. Okay, so it's neither increasing nor decreasing, and hence it's not monotone. Alright, so by now we know what is a bounded sequence and what's a monotone sequence. So at long last we are ready to prove this theorem, which was promised earlier. And this theorem says that if a sequence is monotone and bounded, then it's convergent. So we divide the proof into two parts. We'll first handle increasing sequences, and then we will handle decreasing sequences, because if it's monotone, it can be either increasing or decreasing. Okay, so let's consider the case first where an is increasing. Okay, the sequence is increasing. So the terms are growing, but the sequence is also bounded. So it has to stay below bound, and so it cannot sort of keep increasing, but at some point it has to turn. Okay, and then it has to approach something. Well, what does it have to approach? Well, the least upper bound, right? That's our intuitive feeling. And let's now prove that. Okay, so what I'm going to show is that in fact, when the sequence is increasing and when it's bounded, then the limit of this sequence is in fact the supremum of the set containing all the terms of the sequence. So let's define this set S. You just put in all the terms of the sequence in that set. Okay, so this set contains A1, A2, A3, and so on. Now this set is clearly non-empty, A1 belongs to it, and it's bounded. Why is it bounded? Well, we had seen a little while ago that when the sequence is bounded, then one of the characterizations was that this set is bounded. Okay, that was a theorem that we proved in the last lecture. So the set is non-empty and it's bounded. So by the least upper bound property of R, we know that the supremum, the least upper bound of this set, exists. And now my claim is that this sequence is actually convergent with limit being this supremum. So how do we show that? Well, what do we have to show? Given any positive epsilon, we want to produce an index, capital N, such that if I go beyond that index, then the distance of the nth term to the claimed limit, which is the supremum of S, is smaller than epsilon. So how do we produce this capital N? Well, you see, if I have this epsilon and if I reduce this supremum by that epsilon, then we know that that can't be an upper bound, because this was the least upper bound. So there must be an element which prevents it from being an upper bound. So there must be a term of the sequence which goes above that supremum of S minus epsilon. But then since the sequence is increasing, all the rest of the terms will be above that value, and so they will be close to the supremum of S within the distance of epsilon, and anyway it cannot go above that, right? So that's the only inequality we have to worry about, and let's carry out the proof carefully now. Okay, but the idea is clear. So what we do is, given this positive epsilon, okay, suppose you look at the number supremum of S minus epsilon. So that's a number less than this least upper bound. So this cannot be an upper bound. Since it's not an upper bound, that means that there must be some element of S which prevents it from being an upper bound. There must exist some index capital N such that this term from that set, okay, A capital N, prevents this number from being an upper bound. In other words, it's strictly bigger than supremum of S minus epsilon. Now, because we have this thing, we will use this inequality now to show our desired conclusion. So we have that for every little n which is bigger than capital N, since the sequence is increasing, a little n is bigger than or equal to a capital N, which we know is strictly bigger than supremum of S minus epsilon. And now we are almost done, because from here you get the fact that supremum of S minus an is less than epsilon. In other words, the distance of an to supremum of S is less than epsilon. Okay, and that was the key inequality. So now let's complete the proof, namely that for every little n bigger than capital N, you have that the distance of an to supremum of S Okay, now here we should mention what we had earlier noticed, that you see that an is always less than or equal to the supremum of s. Why? Because supremum of s is the least upper bound, in particular an upper bound. So an is less than or equal to this, right? Which means that an minus the supremum of s is less than or equal to 0, right? And so the mod of this is supremum of s minus an. Okay, so because of that we have got this, and now we have the inequality that we need, because supremum of s minus an we had already observed supremum of s, and if I bring this an to this side and bring this epsilon over to the other side, you have supremum of s minus an is less than epsilon. So we have got our desired thing. So what have we got? Well, given any epsilon positive, we produced this index n. How did we produce the index n? Well, we looked at supremum of s minus epsilon. That can't be an upper bound, so there must be an index capital N which prevents that from being an upper bound, in that a capital N is bigger than that number. And once we have got that capital N, then we showed this thing and verified that our inequality is true. So this capital N was produced by way of this not being an upper bound. Okay. So given an epsilon positive, we produced the capital N in this peculiar way, and then we checked that for every little n bigger than this capital N, the distance of the nth term to the claimed limit is less than epsilon. So we have shown this claim that this sequence converges to this supremum of S. And this takes care of the case when the sequence was increasing. Now let's take care of the case when the sequence is decreasing. Okay. Now a similar proof can be given, but rather than do that, we will just use this case in sort of clever way to get the desired conclusion. So the key observation is that if you have a sequence which is decreasing, and I simply multiply each of the terms of the sequence by -1, then you have a new sequence which is in fact increasing. Okay, and then we are back in case 1, because if it's increasing and bounded, then we know something, namely that it converges to the supremum of the set containing the terms of the sequence. But in one of the exercises we had proved this relation, that if a set of real numbers is bounded and you look at the new set, which is obtained by taking the negatives of each of the elements of the set, so you look at the supremum of minus s, okay, then that's the same as minus the infimum of s. Okay, and we'll use that result to somehow deduce the convergence also in this case. Okay, so let's do the steps. So suppose our sequence is decreasing. That means that a1 is bigger than or equal to a2 is bigger than or equal to a3, and so on. Then I look at the new sequence minus an, and that is increasing, because if I multiply throughout by -1, all the inequalities will be reversed. So I have minus a1 is less than or equal to minus a2 is less than or equal to minus a3, and so on. So this new sequence is increasing. Moreover, it's bounded. Why is it bounded? Because the mod of minus an is the same as the mod of an, and since the sequence an was bounded, we had some bound, and that same bound serves for this new sequence as well. So the sequence is increasing and bounded, which means we are in case 1. Okay, and so this new sequence minus an is convergent to what limit? Well, the supremum of the terms of the sequence. Well, the terms of the sequence are these minus ans. Okay, but this set with all the minus ans is exactly the set which is obtained from this set S by taking the negatives of the elements of the set. So, right, so this set over here is exactly minus S. Okay, and in the exercise we had shown that the supremum of this minus S is equal to minus the infimum of the original set in question. So this new sequence is convergent with limit minus the infimum of S. And then we are almost done, because if you actually write down what this means, you will see that this is telling you something about the convergence of the original sequence. Okay, so given any epsilon positive, since this sequence is convergent with limit minus the infimum of S, there exists an index capital N such that beyond that index, the distance of the nth term, which is minus an, minus the limit, which is minus the infimum of s, is less than epsilon. But you see, if I take minus as a common factor, then this minus and this minus can be taken out as a common factor, and then I will still be left with only one minus, namely this one, right? And then the mod of this is the same as the mod of an minus the infimum of s. So what we have actually got is that no matter what epsilon positive is there exists a capital N such that beyond that n, the distance between an and the infimum of s is less than epsilon, which is exactly the same as saying that this sequence is convergent with limit infimum of s. And that's what we wanted to show. We wanted to show that this sequence is convergent, and in fact it's convergent with this limit. Okay, so that completes the proof of this theorem, and let's consolidate our knowledge. So what we have just shown is that bounded and monotone implies convergent, and we have also seen that convergent implies bounded, but bounded does not imply convergent. And we had just mentioned an example, namely this alternating sequence is bounded, but we had seen that it's divergent, so it's not convergent. So this implication is not true. Bounded alone does not imply convergent. What's the status with just monotonicity? Suppose you forget the boundedness part. What can we say about implications? Well, neither of the implications is true. So monotone does not imply convergent. So for example, if you just look at the sequence of natural numbers, that's an increasing sequence, hence monotone, right? But it's not convergent, because if it was convergent it would be bounded, but it's not bounded. Similarly, convergent does not imply it has to be monotone. Okay, so for example, if you look at this sequence, okay, with the alternating signs, minus 1 to the power n divided by n, we had seen it's not monotone, and in fact let's see that it is convergent. Okay, so convergent does not imply monotone. So let's see an extra example, namely this one, where we claim that this is in fact convergent with limit 0. So to prove this claim, what do we have to show? We have to show that given any distance epsilon positive, there exists an index capital N, such that beyond that index, the distance of the nth term, which is this, minus the limit, which I'm claiming is 0, is less than epsilon. But you see, the mod of this, then this will not be seen, and you just have 1 by n, and then that's a calculation that we had done earlier. You see, if I use the Archimedean property to produce this capital N such that capital N times epsilon is bigger than 1, then for every little n which is bigger than this capital N, you have that 1 by n is less than 1 by capital N, which thanks to this is less than epsilon. Okay, and so we'll get the distance is less than epsilon. Okay, so let's complete the proof. So let epsilon be positive, and let capital N be such that capital N times epsilon is bigger than 1. This is guaranteed by the Archimedean property. And then for every little n bigger than this capital N, the distance of the nth term to the limit is 1 by little n, which is less than 1 by capital N because of this, and that's less than epsilon because of this. So this is an example of a sequence which is convergent but not monotone. Yeah, recall that it is not monotone because you have it's not decreasing because the second term is actually bigger, and it's not increasing because the third term is actually smaller. Let me give you one example of the theorem that we just learned, namely bounded and monotone implies convergent, to deduce the convergence of this sequence whose nth term is given by this partial sum 1 plus 1 by 2 square plus 1 by 3 cube plus 1 by n to the power n. In the last lecture, while discussing boundedness of sequences, we had checked that this sequence is in fact bounded, and the way we did this was, we overestimated this by making use of the sum of a geometric series. What we did was we noticed that 1 by 3 cube is less than 1 by 2 cube, and so on up till 1 by n to the power n is less than 1 by 2 to the power n, and then we had noticed that these terms are in geometric progression with the common ratio half, and we know something about the sums of geometric progressions, we had done some arithmetic, and then we had discovered that, well, 1 plus a half then serves as an upper bound. Okay, so the sequence is bounded, and it's also monotone, you see, because an plus 1 minus an, all the previous summands will cancel, leaving just 1 by n plus 1 to the power n plus 1, and that's positive. So the terms of the sequence are increasing, and it's bounded, and so by the theorem that we just proved, it is convergent. So what does it converge to? Well, it converges to this number L, which is the supremum of this set, in which we have put in all the terms of the sequence. So 1 plus 1 by 2 square plus 1 by 3 cube plus 1 by n to the power n, where the n ranges over the natural numbers. And we just remark that actually it's not known if this L is rational or not. That's an open problem. Okay, so this sequence we have managed to show is convergent without knowing its limit, but by just observing that the sequence is bounded and monotone. To summarize now, if we think of the set of all convergent sequences and we put it in this box, in this green box, then that's contained in the set of all bounded sequences, which is this red box, because every convergent sequence is automatically bounded. But not all bounded sequences are convergent. For example, we had mentioned that this alternating sequence is certainly bounded, but we had seen that it's not convergent. Okay, and on the other hand, we have this blue box containing all the monotone sequences, which is sequences which are either increasing or decreasing, and not all monotone sequences are bounded. For example, if I look at the sequence of natural numbers, then that's increasing, hence monotone, but it's not bounded. And if you look at the intersection of monotone sequences and bounded sequences, okay, so the intersection of this red box and this blue box, then we get this pink region, and these are sequences which are bounded and monotone. And then we have just proved this theorem which says that then they have to be convergent. So it has to be contained in this green box, right? And as we have depicted here, that this pink region is inside this green region. And we have also seen that not every convergent sequence has got to be monotone. So we had given this example, which is minus 1 to the power n divided by n. So that's a sequence which converges to 0, but it is not monotone. And the next topic that we are going to look at is on the algebra of limits. This roughly says that if you algebraically combine the terms of several convergent sequences, then we get a new sequence, right? And that new sequence is also convergent, and its limit is the same algebraic combination of the respective limits. Okay, so this is of course the rough statement, but here is an example. Suppose I know I have three convergent sequences, an, bn and cn, and an converges to a, bn converges to b, and cn converges to c as n tends to infinity. Okay, and suppose I form a new sequence whose nth term is this complicated algebraic combination of an, bn and cn. I square an and then multiply bn and cn and then divide by this number 1 plus an square plus bn square plus cn square. Okay, so it's some rational combination of these three things. Then it turns out that that new sequence whose nth term is given by this in fact converges to an square will converge to a square, and b and cn will converge to b times c, and so if I just had the numerator, that would converge to a square plus b times c, and the denominator converges to 1 plus a square plus b square plus c square, and so this whole thing converges to a square plus b times c divided by 1 plus a square plus b square plus c square. Okay, so whatever algebraic manipulations you did to get this term from the an, b and cn, the same manipulations you do with the limits, and that will be the limit of this sequence. Okay, so this is quite a powerful theorem because it allows you to deduce the limit in a very simple manner. Okay, so to consider a more concrete example, Suppose I have a sequence whose nth term is given by 3n to the power 4 plus 9n minus 1 divided by n to the power 4 plus n square plus 1. Well, what we observe is that if I take n to the power 4 as a common factor, then you see I'll be left with 1 by n to the power to some power, and 1 by n is a sequence that I know a lot about. We know that it's convergent with limit 0, right? So that's the idea. You view this nth term as a combination of simple terms, and in this case it's obtained by taking n to the power 4 as a common factor in the numerator and the denominator. So then the numerator becomes n to the power 4 and then 3 plus 9 n by n4, which gives 1 by n cube minus 1 by n4. And in the denominator, if I take n to the power 4 as a common factor, I get 1 plus 1 by n square plus 1 by n to the power 4. So these two cancel, and then I'm left with 3 plus 9, 1 by n cube minus 1 by n to the power 4. And similarly here you have 1 plus 1 by n square plus 1 by n to the power 4. And I know that 1 by n, the sequence with the nth term 1 by n, is a convergent sequence with limit 0. So the nth term of this sequence is really obtained from 1 by n by doing this algebraic manipulation, and you do the same algebraic manipulation with the limits. So this will converge to 3 plus 9 times 0 cube minus 0 to the power 4 divided by 1 plus 0 square plus 0 to the power 4, which is equal to 3. So we know that this sequence actually converges to 3 as n tends to infinity, okay, which is quite remarkable. So this method, this algebra of limits, although it is sort of a simplistic looking statement, it is quite a powerful theorem, because to prove that this sequence is convergent to 3 using brute force epsilon deltas will be quite cumbersome, but somehow with this algebra of limits it's quite straightforward. So this was just motivational remarks, so we have not been precise about what we exactly mean. So now here comes the theorem. Okay, now this theorem, in the notes I have given a long list, but I have broken it into sort of two parts, and we'll just do the first part today, and the next part we'll do next time. Okay, so what I want to show today is that if you have two convergent sequences and I take their term-wise sum or term-wise product, then you get a convergent sequence too, and the limit is then either the sum of the limits or the product of the limits. Okay, and then there are some corollaries which come from this statement number 2. Okay, so that's all I want to show today, and then there are two more other statements in that theorem which we'll do next time. So this theorem says that if an and bn are convergent sequences, then the following is true. So the first statement is that if I take the term-wise sum of these two sequences, so I take the new sequence whose nth term is given by the nth term of this sequence and the nth term of this sequence, and you add them up. Okay, so that's the nth term of this new sequence. That's sometimes referred to as the term-wise sum. So you take the term-wise sum of these two sequences. So that new sequence is also convergent, and in fact the limit of this new sequence is the sum of the old limits. The second statement is, if we, instead of taking the term-wise sum, if I take the term-wise product, so the new sequence whose nth term is given by a and bn. So what are the terms of this sequence? Well, a1 b1, a2 b2, a3 b3, and so on. That new sequence is also convergent, and in fact the limit is the product of the original limits. And then we will also show that if I scale this sequence by a real number c, then the limit is also scaled. And actually this follows immediately from item number 2 by taking the other sequence bn as the constant sequence c, 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 right? Because then their term-wise product is can, and by this the limit of can will be the limit as n tends to infinity an times the limit of this constant sequence c, 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 which is equal to c, right? And so we get this. And the fourth statement, so 3 immediately follows from 2. And the fourth statement is that if for any fixed natural number I look at an to the power k, Okay, so for the terms of the sequence are a1 to the power k, a2 to the power k, a3 to the power k, and so on. So that sequence is also convergent, and in fact the limit of this kth power, term-wise kth power, is the kth power of the limit of the original sequence. And this also follows from 2 by, first, for example, if k was 2, then I simply take an and bn as the same sequence. So then you'll get limit of an square. Okay, the sequence obtained by squaring each of the terms is the limit as n tends to infinity of an times the limit as n tends to infinity of an, right? Because bn has been taken to be equal to an. So you get the limit as n tends to infinity of an square. And you can then give an inductive proof. You can also get an cubed by taking bn as an square, and so on. Okay, so this statement number 4 also follows from statement number 2. So the real task is just to prove statements 1 and 2, that the term-wise sum of convergent sequences is convergent, with the limit being the sum of the limits, and the term-wise product of two convergent sequences is convergent, with the limit being the product of the limits of the individual sequences. So let's start with the term-wise sum. So what do we have to do? Given an epsilon positive, we have to produce an index capital N such that beyond that index, the nth term, which is an plus bn, minus the limit. So if I call the limit of this sequence an as a and the limit of this sequence bn as b, then we are claiming that the limit is a plus b, right? So what we have to do is to look at the distance of the nth term, which is an plus bn, to the limit, and make sure that that can be made small if I go far enough in the sequence. So let's first hatch a plan of how to do this. So you see that this an plus bn minus a plus b can be rearranged to read an minus a plus bn minus b. And I know that an can be made close to a, so this can be made small, and bn can be made close to b, so that this can be made small. So the obvious thing to do is to use the triangle inequality. I know that this can be made small if I go far enough in the sequence, and this can be made small if I go far enough in the sequence. So of course the sum can be made small too. To make things very precise, if an epsilon would be positive is given, then it would be great if each of these can be made smaller than epsilon by 2, because then this is less than epsilon by 2, this is less than epsilon by 2, so that sum is less than epsilon by 2 plus epsilon by 2, which is epsilon. Okay, so that's the idea, that you first choose an index so that this is smaller than epsilon by 2. You choose an index such that this is smaller than epsilon by 2, and then you take the larger of these two indices, so that beyond that, then we are guaranteed that each of these is less than epsilon by 2, and hence their sum is less than epsilon. So that's the plan. And now let's write it down. So this is typical in analysis, that we first do some rough work to make a plan, and then we write it down. If I had just shown you the proof with this epsilon by 2s, you would be wondering, where did the epsilon by 2 come from? Well, there's nothing sacred about epsilon by 2. We just choose it so that, well, then each contribution is less than epsilon by 2, so their sum is less than epsilon. Okay, but you could have chosen epsilon by 3 or anything, some other reasonable thing over here. Okay, so the choices are also not unique often in analysis. Okay, a lot of things work. With this plan in hand, let's carry it out. So let epsilon positive be given, then epsilon by 2 is also positive, and let the limits of these two sequences be denoted by a and b respectively. Now since epsilon by 2 is a positive number, with this distance there exists an index, let's call it na, such that beyond that na, the distance of the nth term to a is less than epsilon by 2. And similarly, since this other sequence converges to b, with this challenge distance, there exists an index, let's call it nb, such that beyond that nb, the distance of the nth term to the limit is less than the challenge distance, which is epsilon by 2. Right, so now we have this yellow thing holding whenever little n is bigger than na, and we have this pink thing holding whenever n is bigger than nb. Okay, so if I take capital N as na plus nb, or also you could have taken the maximum of na and nb, okay, nothing sacred about taking their sum, but sum works. And then we have that whenever little n is bigger than this capital N, this little n is certainly bigger than na, and it's also certainly bigger than nb, so this yellow thing and this pink thing both hold. So whenever the little n is bigger than capital N, we have that the nth term of our sequence of interest, namely an plus bn, minus the claimed limit, that distance, is equal to, we can rearrange this sum as an minus a plus bn minus b, and then using the fact that the modulus of the sum is less than or equal to the sum of the moduli, the triangle inequality, we have that this is less than or equal to mod of an minus a plus mod of bn minus b. But as we had just mentioned, when n is bigger than this capital N, it's bigger than Na, so this yellow thing is less than epsilon by 2, and likewise then n is also bigger than nb, so this pink thing is true, so that this is less than epsilon by 2 too. Their sum is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. And so what have we done? Given any epsilon positive, we have produced a capital N. How did we do the produce this capital N? Well, we first produced an Na because of the convergence of this sequence, then we produced an Nb because of the convergence of this sequence, and then we produced a capital N by plugging these two together, using these two. You took Na plus Nb, and then for all little n bigger than capital N, we managed to prove that the nth term minus the claimed limit, the distance of that, is less than epsilon. So we have checked the statement of the definition of convergence, and so we can conclude that the limit as n tends to infinity of an plus bn is equal to a plus b, but a is the notation for this limit and b is the notation for this limit. So if you substitute that, then we have got this theorem. Okay, so we have showed that the term-wise sum of convergent sequences is convergent, and then the limit is the sum of the original limits. Now we want to prove statement number 2, which is about the term-wise product of two convergent sequences and that being convergent. Okay. So again, we first have to do some rough work. Okay, so we start by looking at our goal. The goal is to make a and bn close to ab. And what I know is that an is gets close to a if I go far enough, and bn gets close to b if I go far enough. And somehow I want to show that a and bn comes close to ab. Now it's a little bit annoying that you can't really, I would have liked to take bn as a common factor over here, because then I would have got an minus a, about which I know something, that it can be made small. So that is not possible here. So what I do is I artificially create a term so that it becomes possible, and this is sort of a standard trick in analysis. Okay, so often you introduce terms so that you get to see a combination about which you know something. So what I'll do is I'll subtract the term abn. Why do I do that? Because then bn is a common factor and then I get an minus a, about which I know something. But I'm not allowed to just subtract terms willy-nilly. I have to then add plus a bn, so that then the net effect is 0. You see, these two cancel each other, and this old term I should not forget. You have minus ab, which stays put. Okay, so what I've really done is just added 0, because the combination of these two goes away. And it's just as well that we introduce this term, because not only is this combination very good, but also over here then a comes out as a common factor, and then I get bn minus b, about which I know something, that can be made small. So this whole thing is equal to, if I carry out taking bn as a common factor, I get an minus a times bn plus a times bn minus b. And then I use the standard trick of using the triangle inequality. So the mod of this is less than or equal to the mod of the first part, but that's the mod of this thing multiplied by the mod of this thing. And then the mod of the second part, which is again the mod of the first thing, mod a, times the mod of bn minus b, because mod of xy is mod x times mod y. That's what I'm using in order to simplify the mod of each of these summands. This is quite good, because I know that mod of bn minus b can be made as small as I please if I go far enough in the sequence, and mod a is just a number, so that's harmless. But over here I'm a little bit worried, because you see that mod of bn, I don't know its behavior as the n changes. Can it grow? Because this is certainly becoming small, but what if that smallness is ruined by something growing? Well, it can't grow, because bn is convergent. It's in particular bounded, and so we know that this is bounded by some big number. right? And then that's good, because once there is some fixed number over here, then since this is going to 0, this combination will also go to 0. So this whole thing can be made small. Now again, it would be great if the contribution of this is less than epsilon by 2 and the contribution of this is less than epsilon by 2, so that their combined thing is less than epsilon, and then we are done. So how to make this less than epsilon by 2? Well, this m is a positive number, and so of course I can make this smaller than epsilon by 2m. Why not? After all, I know that the sequence is convergent to A, and so I know that given any positive number, in particular this one, yeah, I can produce a large enough, I know that there exists a large enough index such that beyond that, this thing is less than epsilon by 2m. And that's great, because then this m will cancel, leaving a contribution of epsilon by 2. And over here we can do a similar thing. So here, ideally, to get this contribution less than epsilon by 2, the contribution of this should be less than epsilon by 2 mod A, because then the mod A's will cancel. Except, you know, this sequence an could have limit 0, and if I had mod A, only mod A in the denominator, I would be dividing by 0, which is of course not allowed. And so in order to prevent this from being 0, to this non-negative thing I add 1. Does it spoil things? Not really, because if this thing is less than epsilon divided by this one, then you see mod A divided by mod A plus 1, that fraction is less than 1, and then I'm left with epsilon by 2. So this whole thing is going to be less than epsilon by 2. And so this is less than epsilon by 2, this is less than epsilon by 2, and that together would be less than epsilon. Okay, so that's the plan. And to carry out this plan, we have done some rough work, and now we give the details. So somewhere down the line, I'm going to use the fact that this sequence Bn being convergent is bounded, and I'll use this bound. So let's at the outset declare that as the bound. So since the sequence Bn is convergent, it is bounded, and let capital M be a positive number such that that serves as the bound. So mod of Bn is less than or equal to m for every natural number n. Now suppose we are given an epsilon positive. Then we know that epsilon divided by 2m, m is positive, that's a positive number, and epsilon divided by 2 times mod A plus 1 is also a positive number, right? Because I'm first of all dividing by something non-zero, and moreover dividing by something positive. Since the sequence an is convergent with limit a, I know that there exists an index, let's call it na, such that beyond that index, the distance of an to a to the limit is less than epsilon by 2m. Okay, so I'm doing this part now. This is less than epsilon by 2m. Okay, so we record that. And since the sequence Bn is convergent with limit b, I know that there exists an index nb such that beyond that index, the distance of Bn to b is less than this positive number. Okay, so that I'm doing this part. And now let's take capital N as the sum of Na and Nb, and then whenever little n is bigger than capital N, I know that this is satisfied and also this is satisfied, so I'm allowed to use these highlighted inequalities. So now we sort of repeat this. The mod of An minus An Bn minus AB, so this is the sequence that we are investigating the convergence of, and this is the claimed limit. So I'm looking at the nth term minus the limit, the distance. That is equal to, I add and subtract this term. So effectively I'm adding 0, doing nothing to it. So I do minus ABN and plus ABN. And then the nice thing is that I can take Bn as a common factor. So I get An minus A times Bn. And here I take A as a common factor. So I get A times Bn minus B. And by the triangle inequality, this is less than or equal to the mod of this one plus the mod of this one. The mod of this one, since mod xy is mod x times mod y, this is the mod of this times the mod of this. And similarly, the mod of this one is the mod of A times the mod of Bn minus B. And since little n was bigger than capital N, then in particular it's bigger than Na and Nb, so we are allowed to use these highlighted inequalities. So because of that, I know that this thing is less than epsilon by 2m, and this thing is less than epsilon by this thing. Okay, and now the m cancels conveniently, and mod a divided by mod a plus 1 is less than 1, and then moreover I'm left with epsilon by 2, so I get that this is less than or equal to epsilon by 2 plus epsilon by 2, which is epsilon. So given any epsilon positive, I have produced a capital N such that beyond that N, the distance of the nth term to the claimed limit is less than epsilon, And so we have proved that the term-wise product of convergent sequences is convergent, with the limit being the product of the limits of the original sequences. And as we had mentioned, then it also follows that if you scale a sequence, a convergent sequence, then the new sequence you get is also convergent, with the limit being the scaled limit. And this just follows from the second statement by taking Bn as the constant sequence C, which is convergent with limit C. So then when Bn is always C, you get exactly that this An Bn is Can, and the limit of that will be the product of the limits. Well, the limit of An is the same, but the limit of the constant sequence C is C. And so that we had seen in the last lecture, and so we get this from this one. And similarly, this item number 4 follows from item number 2 by an inductive argument. You do induction on K. And there are two more statements in this algebra of limits, and that we'll do next time. So one of them says that whenever a sequence is convergent and you take the absolute term-wise absolute value, okay, so the new sequence, which is mod a1, mod a2, mod a3, and so on, that sequence is also convergent, and in fact the limit is the modulus of the old limit. And the second statement is that if each of these ans were non-zero, and also if the limit was not zero, then the new sequence, which is obtained by taking the reciprocals. Now, taking reciprocals is allowed because none of the ans are zero, so this is well defined. So that is also convergent, and in fact the limit of this reciprocal sequence, term-wise reciprocal sequence, is the reciprocal of the limit. Okay. So these two we will do next time, and we will stop here.